Okay, now our job today is to learn how to determine the molecular geometry of covalent compounds. And so let's do this with using a simple example of, let's start off really simple with CH4. And so in this case, we have a really simple molecule, and so this will always follow hunk. And so this is what we could do to draw this. And so we'll use that as our starting point. So whenever we figure out the molecular geometry of a compound, our first step is to draw the loose dot structure. And so in this case, we have a really simple molecule. We have carbon with 4 hydrogens attached to it. Then our job is to then determine how many things are attached to the center by doing something called finding how many electron pairs we have. Oh my god. And so the way we calculate how many electron pairs we have, so electron pairs is equal to your number of bonds plus your number of lone pairs. And so if we look at this, this is always towards your central atom. And so in this case, our central atom is carbon, and so we're only looking at carbon. And so let's count how many electron pairs we have for carbon. So electron pairs, I like to derive that as EP, electron pairs, is equal to, for carbon, is we have 1, 2, 3, 4 bonds associated with this carbon. And then we have 0 dots attached to our carbon. And so we have 0 lone pairs. And so we have a total of 4 electron pairs. And then the only other piece of information that's really important is that we know that we have 0 lone pairs, right? And so I like to describe that as LP, as 0, or that we have 0 lone pairs associated with our carbon. From that information, what we could do is use the chart to figure out the molecular geometry of this molecule. And so in this case, what we could do is we have 4 electron pairs and 0 lone pairs. And so all we have to do is match that from the chart. And from the chart, if we have exactly 4 electron pairs and 0 lone pairs, we have what we call a tetrahedral molecular geometry. And this is our molecular geometry of our molecule. And so if I asked you to redraw this, we'd have to recreate this by having our center. So if you look at the molecule that's drawn in the chart, we have E, X, X, and then we have a wedge for an X out here, and then we have a dash for an X back here. All we have to do is convert our drawing, our letters, or our elements that we have in here to match our molecule or basic drawing that we have in the chart. And so instead of it being an E in the center, we have a carbon. And instead of having X's all around it on the outside, we have H's all around it on the outside. And so we just recreate this with H's on the outside. And so this is a tetrahedral molecular geometry. So what if we did this once again with a slightly harder or more challenging molecule? Let's say we have CH2O instead. Once again, our first step is to draw the LDS. And so we have to figure out how to draw this LDS. In this case, we still have a simple molecule. And so all we have to do is follow honk. And so that's 1, 2, 3, 4 bonds. And so once again, our central atom is always our first element, or almost as always our first element. So we have carbon. And then we have two hydrogens. So I'll just draw them one above and one below. And then we have an oxygen, and that needs two bonds, and our carbon needs two more bonds. And so we add a double bond between that and the oxygen. And then we add our lone pair of electrons to our oxygen so that, remember, all elements besides H need 8 electrons. And so this is our loose dot structure of CH2O. Our second step, once again, is find how many electron pairs we have. And so in this case, once again, we look at only our central atom. So we're only looking at C and how many electron pairs we have. Remember, electron pairs is equal to number of bonds plus your lone pairs. When it comes to bonds, though, a single, double, and a triple bond only count as one electron pair. So you could think of it as electron pairs as how many things are attached to the center, right? Or how many things are attached to the central atom. And so if you think about it that way, right? So if you look at our carbon, we have one letter here, one oxygen, and two hydrogens to make a total of 3 things attached to it. And that would be how many electron pairs we have. But if we looked at and counted all single, double, and triple bonds as just one EP, we could just count how many of those we have. So this is one bond right here. We have 2 bonds here, our second single bond. And then remember that this double bond right here, that counts as just one electron pair. And so we have a total of just 3 electron pairs or 3 bonds. And then we still have 0 dots associated to our carbon. Remember, lone pairs only are on the central atom. Central atom only. So even though there are lone pairs or dots associated with our oxygen, since oxygen is not the central atom, we do not count these dots. So if there are H's or dots on these H's, those would also not count towards our electron count. And so in this case, we have a total of 3 electron pairs. And then once again, our lone pairs associated to carbon is 0. And so all we have to do is use the chart to determine the molecular geometry of this. So we have electron pair 3 or 3 electron pairs and 0 lone pairs. And if we use the chart, this is equal to a trigonal planar molecule. And so if I asked you to redraw this, we would have to redraw this as such. And so if we looked at the example, it's E has an X down here, has an X over here, and an X up here. And so all we do is rearrange it so that our central atom is still C. We have 2 hydrogens attached to it. It doesn't actually matter which X we replace as hydrogens. So we could just have one right here and one right here to make it simple. And that even though this drawing only has a single bond, it could also be drawn as a double, maybe even a triple bond. And in this case, we have a double bond between carbon and oxygen. And so we redraw that as a double bond with oxygen. And then we keep the dots consistent over here. And this is what we have, which is a trigonal planar molecule. And so anytime we have a really simple molecule with molecular geometry, just use honk, and then we could use that to draw this as a molecular geometry diagram.